Welcome everyone. Thank you so much for joining us today. Conscious we've got lots of ground to cover, so I'll start by introducing. So welcome to the Enabling Water Smart Communities Spring 2026 webinar series. My name is Charlotte from Anglian Water and I'll be chairing today's session. This is, in fact, the first of our spring webinar series, and today we'll be delving into the Designing Low Demand Networks project, which makes up one of the projects in the final tranche of the Enabling Water Smart Communities programme, and we'll be exploring the key findings and recommendations from the work to enable us to develop future-proof design criteria for drinking water and sewer systems in new water-efficient housing developments. So before we do delve into the details, I'll just run through some housekeeping. So this meeting will be recorded. If you do have any objections to the session being recorded, please do let us know. There's no obligation for you to turn your cameras or microphones on. It's just for the speakers. However, we may ask you to come in at the end when we are doing the Q&A, should you have any questions. If you do experience any technical issues and need assistance, please do raise your hand or use the chat feature on Zoom, so you can let us know and we can support you. We have got Nathan here to support with any technical queries and he is monitoring the chat. So as mentioned, we will take your questions at the end of the presentation, but should you have any burning questions in the meantime, then you can use the Q&A facility on Zoom, and please do use this facility over the chat facility so we have visibility of these, and when you do ask a question, it would be great if you could state who you are posing the question specifically to. So moving on to the speakers, so a little bit about me. As mentioned, I work for Anglian Water. I sit within the innovation team and I'm the project coordinator on the Enabling Water Smart Communities programme, and I have been since the end of 2024. Anglian Water are the lead delivery partner of driving the Enabling Water Smart Communities programme. But today I am joined with several colleagues at Arup, who are a key delivery partner on the programme and have delivered the Designing Low Demand Networks project. So starting with Liliana, who has led this project and is a senior digital water consultant at Arup, working across a wide portfolio of digital and innovation-driven projects in the water sector. Liliana holds a PhD in water management and completed a postdoctorate fellowship focused on water conservation and circularity in urban water systems. And we also have Olivia joining us today, who's a senior consultant at Arup's digital water team, working on a range of digital projects for the water sector. Olivia's background, I believe, is in chemical engineering, and her PhD was focused on water conservation in sewerage systems. And Olivia led the delivery of our Impact of Reduced Flows on Sewers project, which took place within a previous tranche of the Enabling Water Smart Communities programme. And Olivia will be telling us a bit more about that shortly. And last but by no means least, we have Vicky with us today. Vicky is the digital water leader for Arup and has nearly 30 years experience in delivering digital and data projects in the water sector. Vicky sits on the Enabling Water Smart Communities Independent Programme Board as well as the project steering group. So moving on to the agenda. So I'll quickly run through. So I will shortly hand over to Vicky, who will be providing an overview of the Enabling Water Smart Communities programme. And then Olivia will be summarising the work that was conducted during the earlier phase of the Enabling Water Smart Communities programme, looking at the impact of low flow on sewerage systems. Liliana will then introduce the Designing Low Demand Networks project, discussing how and why the project has been undertaken and how it does build upon the initial phase of works. And then Liliana will, of course, summarise the findings and recommendations that have been identified to inform future design standards. And then it'll be back to me to conclude by letting you know how you can continue to engage, what the next steps are for the project and EWSC as it draws to a close, and then it will be time for the Q&A. So without further ado, I will hand over to Vicky for the overview of the Enabling Water Smart Communities programme.
Good afternoon, everyone, and welcome to the first part of our webinar series, which is going to be talking about our work around designing low-flow networks. If we could move on to the next slide. I'm going to be quite fast in delivering this because hopefully if you've attended before, that you'll know that this is an Ofwat Innovation Fund project that's been now running for 4 years, and it explores the relationship between water management, communities and housing development. And what we'd want to do is unlock new opportunities to make sure there's good cross-sector delivery. And it's really important that we highlight the areas that we've considered is around the stewardship of the assets around the whole water cycle. The project delivery team is set out below. The main water companies in there with Anglian in the lead position, but we're very grateful to be supported by United Utilities and Thames Water on this project. And you can see that we've built a really strong set of partners and collaborators on this. And we are hoping and envisaging that this is going to continue for some time to come, and Lottie's going to give you an overview on our hopes and dreams for that. Next slide, please. I always want to say what is a water smart community, and it is about placemaking. And what we want to do is to ensure that water is central to design and how we embrace the principles of water stewardship in new housing development, and that we can get empowerment across the assets and systems. We want people to use water wisely, and we also want to take care of the environment. And the feature of the work we've been trying to do is on enabling. So this project has also been setting out the direction and action that we want to take to ensure that we can get water smart communities happening through the whole of England and Wales. Next slide, please. We always have to give a kind of overview around what is integrated water management, but this is all about how we access all the steps through the water supply chain, from the very catchment through the distribution treatment works, the strategic green-blue infrastructure, what water-sensitive urban design looks like, and also how we engage people, community, information and the economy. And it's to give wider benefits around there in terms of place, health and well-being, livelihoods, critical infrastructure, and how it supports food and agriculture and habitat and biodiversity. And this is a real feature throughout the project, that this is a systems level change project. And what we have been doing is engaging across that in enabling system level change throughout the water cycle. And we have some successes to that degree, but the journey goes on. The session today looks very much at the distribution network system here, and it's often the hidden and unloved part of the network, but we want to bring it out and give it the most love and say, why should we look at the new future of design in water networks and wastewater networks? Because lots of our talk is about how we must be much more water efficient, and we can't have water efficient homes that are going down to very, very low efficiency without completely looking at the design of our networks. And that's the aspiration of the project. And now I'm going to hand over to Olivia to talk about the work that we've done.
Yeah, hi everyone. Thanks for coming. So I led the kind of first phase of this work that was based around sewerage, and that was kind of concluded about 12 months ago. And then Liliana will talk about kind of where we've come since then. So next slide, please. So I'll start with the problem statement that we were tackling. So we know that widespread water efficiency measures will impact wastewater quality, wastewater composition, solids loading, nutrient loading, wastewater temperature, but those planning water efficiency measures have little understanding of the impacts that that this will have on sewerage infrastructure downstream. So that includes things like blockages, stagnation, treatment efficiency. And so the tools and knowledge for assessing these impacts have been made available through academic research, but we found that it was not in a form that would make it easy to use by the water industry. So that's what we were really aiming to solve with this project. So we aimed to solve this by making the existing research and tools more accessible, working with users to ensure that the tools delivered kind of actionable insights that could really help them do their jobs well. We wanted to develop a tool that was multifaceted to enable kind of communication between different departments and organizations on this issue. And through providing these tools, we hoped to enhance the confidence in decision making and bridge the disconnect between organizations on this issue. Next slide, please, Lottie. So we had three main outputs from the kind of ARUP work streams on this. We also worked with Thames Water, who worked more on the treatment efficiency impact. But these were our work streams. So firstly, we produced a pamphlet that kind of serves as an easy access guide to the existing research on this topic. So that's really kind of the gateway if you're new to the topic. Then we also produced a network model that's open source. So this was the conversion of an existing tool that was in MATLAB. But yeah, obviously MATLAB needs an expensive license and might be difficult to use for some people. So yeah, we converted it into Python, which is freely available open source software. So I'll talk more about that later. And then we also created a rapid assessment tool that is kind of for high level assessment of this issue. So it's a static output of the first tool, but for people that may not be modelers by background. Next slide, please. So I spent my PhD, as Lottie said, exploring this topic and published 3 papers in this field. There's also many others who have published work in this space, including Liliana, who will speak next. But we realized that this knowledge was locked up in academic literature behind paywalls and not very accessible to practitioners. So this pamphlet kind of provides a really accessible starting point to help users to look at the impacts of water conservation on sewage networks. And this is just a little list of the sections that are included. So we kind of outline some approaches to water savings. We look at 5 future scenarios. Outline kind of how variable wastewater is from different appliances and with those scenarios. And then we look for an example network, what the impacts are on the wastewater for those scenarios. Then it also has a section outlining the simulation tools that I'll talk about next. And there are also a list of literature for further reading. So hopefully this will be a really useful resource, and I encourage you to take a look at that. There's a QR code there, and yeah, it's available on the Enabling Water Smart Communities website. Next slide, please. So the network modeling tool that we developed is called PySimDM. It's basically the Python version of SimDM, which is a software that was developed by KWR, which is a research institute based in the Netherlands. So this originally was built in MATLAB, and it's a tool to simulate water use patterns down to very small temporal, down to 1 second, and small spatial scales. So on down to a single appliance. And it's a bottom-up model for water demand, or it was a bottom-up model for water demand. So based on population statistics and the way people use water, it builds up a flow pattern rather than being based on monitoring in the catchment and global assumptions across populations. So for my PhD, I developed the wastewater extension to this software, SimDim Wastewater, which allows the creation of appliance-specific wastewater discharge patterns. Which is more accurate when you're looking at future changes, as you can kind of target specific appliances. So you can look at the impact of switching to low flush toilets or low use showers, for example, and just look how those specific appliances change your profiles. So this software can form the input to network models. So we used InfoWorks ICM, for example, to observe impacts in the network. Yeah, so as I said, these were MATLAB-based tools, and through this project, we completed the conversion into Python, as well as some user improvements to make the tool more accessible for practitioners. Next slide, please. So PySimDM is now available through GitHub, and it's completely open source and allows you to simulate probabilistic water demand and discharge at end use level. So based on population and use statistics, you can build and populate households suitable to your region or scenario. There's also some default data in there if you just want to have a play around. The model simulates flow down to an appliance level, so it can provide information on wastewater quality. So for example, at 7 a.m., the primary water usage is everyone kind of going to the toilet, and therefore water quality present in the network can be associated with the usage at that time throughout the day. Yeah, next slide, please. So SimDim Wastewater serves as the input to InfoWorks ICM, as I said, or another network model if you choose. And the impacts can be viewed in the network. So here, this just shows we've developed a functionality that can read in your shape files with your specific population statistics and property groupings and simulate catchment level flow patterns that match your data. So you don't have to go kind of house by house or anything. It can integrate well with your kind of existing methods. Next slide, please. And so the final tool that I'll speak about is the rapid assessment tool, which is the kind of high level version. It gives a high level overview of how reducing water use might impact flow in small developments. So it's a really simple dashboard tool that uses a static output of PySimDM that can then be overlaid to visualize kind of key information based on what you're interested in. So this tool is primarily to support kind of go, no-go decision making and investigation without the new need for in-depth network modeling. So you can quickly kind of have a look at how switching to 1 liter flush toilets, for example, would impact your flow pattern throughout the day. And it's intended for this tool to support kind of pre-planning conversations between, say, a water company developer or water-only companies. And because we intended this tool for people that deal with water, it might not be water professionals. who might not be water professionals, sorry, we had to make it really easy to use. So, and the parameters that we've included were informed by the user testing. So hopefully it includes kind of really valuable parameters that can support conversations and investigations that these people need. Next slide, please. So this is my last slide, and this just shows what the tool looks like. So you can see here that we've created kind of high, medium, low impact scenarios for each household appliance. This means you can kind of easily investigate impacts of changing appliances on your flow pattern, pollution concentration, and water discharge temperatures. So yeah, these scenarios, three scenarios for each appliance were simulated with PySimDM, and then there's like a static output here in the dashboard. So you can see here on the, oh, I don't know what's the left-hand side of the screen. Yeah. There's like a toggle, so you can toggle for each appliance whether you want how kind of dramatic you want to be on your scenario that you're using for each appliance. So if you only want to look at, if you want to have a big impact on your shower flow, but you're going to leave your dishwashers the same or whatever, you can choose what you want to look at. And then you see that kind of reflected in the profiles on the right. So hopefully that gives a kind of flavor of the three outputs that we had from the first part of the project. And as I said, they're all freely available on the Enabling Water Smart community's website. So please go and have a look. And now I'll hand over to Liliana, who's going to talk a bit more about the recent phases of the project.
Thank you very much, Liv, especially thank you very much for explaining SimDium and PySimDium. So now moving into the second part of this webinar, where I would like to focus on designing low demand networks. Next, please. So to start with, just quick numbers on the wider context. The UK, as you must all know, is projected to face a major water supply gap by 2050, 4 to 5 billion liters of water gap, liters per day gap. And climate change is also expected to put significant pressure on summer river flows, and that is especially happening in already water stressed regions such as South and East England. And on the other hand, around 1.5 million of new homes are planned by 2029, and many of those planned homes are actually going to be built in already water stressed areas. So the mathematics is not that difficult. We need to save water somehow. Next slide, please. One of the most effective ways to close this future supply gap is actually reducing household water demand because homes represent the largest controllable water use sector. At the moment, households in the UK use 140 to 155 liters per person per day. And there is also a new UK policy aiming for 20% reduction in household water use by 2037, and that means that homes will be using less water than today, and that is a positive thing for water stress regions, but it creates a very important engineering challenge, which means that our drinking water and sewer systems are currently designed assuming much higher flows. And the key question becomes, how will our infrastructure perform when demand becomes significantly lower? Next, please. Yes. So to address that question about how our infrastructure will perform, this project followed 4 main steps. So first of all, we conducted a literature review on water conservation, looking at the demand reduction, water efficient technologies, appliances, and future conservation trends. Second, together with stakeholders, wide range of stakeholders, we use the knowledge also from the literature review to develop future water conservation scenarios to be modeled. Third, we use hydraulic modeling to test how water networks behave under these current and also future scenarios. And last but not least, based on the modeling insights, we came up with certain guidelines how we should actually design low demand developments. Next slide. So the first step, as already said, of the project was to build an evidence base. We reviewed scientific literature, but also industry reports focusing on several aspects. Like appliances, technologies, low flow showers, efficient washing machines, dual flush toilets. We also quickly touch upon behavioral drivers of water demand reduction. And we also reviewed policies and regulatory frameworks, including government targets for water efficiency and future demand reduction. And that review basically helped us define future demand scenarios together with our project partners and stakeholders. Next slide, please. Next, we examined how drinking water networks are currently designed. In principle, the primary goal of drinking water system design is to ensure adequate pressure at the customer, sufficient flow, and reliable supply, so continuity of supply, and that must happen also under like peak demand, like morning peaks or during like fire events. And typical design assumptions include maintaining minimum pressure, like a legal minimum of 10 to 15 meters at the customer connection. In terms of the velocities of water in the network, it's very important to maintain at least 0.3 meter per second so that networks can have this self-cleansing capacity and ability to prevent brown water events. And this criteria worked very well, and we need to follow this criteria so that we actually have enough water, but that we also have wholesome water. Next slide, please. Similarly to the drinking water networks, sewer networks are also designed based on certain hydraulic principles. In principle, gravity sewers are designed to ensure that sewer water can be conveyed effectively without causing blockages and surcharging. And the key concept is also like in the drinking water networks, to have this self-cleansing conditions so that flow is strong enough for solids to be transported in order to prevent sediment depositions and further problems. Typical design assumptions include foul flows of around 400 liters per dwelling per day, and self-cleansing velocity, which is at least 0.6 meter per second. In line with that, you also need for sewer networks to have additional parameter, which is called shear stress, to be in the certain threshold range. Next one, please. And what does research show about possible challenges in lower networks? there's a lot of research done on this topic, and actually lower flows in drinking water networks can lead to several operational challenges with lower velocities. You can also increase risk of sediment deposition. Resuspension of the deposited material often occurs when certain threshold, as already said, is met. Water quality deterioration, according to research, significantly increases when water age exceeds 48 hours, 24 to 48 hours, and also typical decay rates of chlorine per day can happen if you have this kind of issues. And last but not the least, biofilm growth. So this slimy thing inside the pipes increases significantly. Velocities are lower than 0.1 to 0.2 meter per second. Next, please. Yes. And similar challenges exist in a sewer system when flow decreases, both velocity and shear stress decreases as well, which, as said, increases the risk of deposition. And over time, that can lead to blockages, auto problems, maintenance issues. What is very important to say, what is on the figure on the right-hand side, is the figure shows how pipe slope influences sewer transport and self-cleansing performance. In principle, recommended slopes, like the one with a green check, allow water and solids to move together effectively, preventing the deposition accumulation of deposits and supporting like the stable flowing conditions in the sewer systems. And if the slope is too flat, solids settle, and then that can lead to many different issues. So in conclusions, flat pipe gradients and oversized pipes can further amplify operational problems in the low flow developments. Next slide. And based on this literature review, together with various experts from various fields, we organized a workshop in order to actually develop scenarios, realistic scenarios to be model adjust for like to explain it a bit. Normally speaking, in research, what we see very extreme water saving scenarios, but with this workshop, we were meant to align on the scenarios to be modeled, like realistic scenarios to be modeled. And basically, we came up with 3 different scenarios. The first scenario represents the near future, per capita consumption 90 to 100 liter per person per day. Second scenario represents timeline around 2040, consumption between 80 and 90, and the lowest is a demand drop 70 to 80. And in principle, with these scenarios, we were able to test how actually water hydraulics performs under lower demand conditions. Next slide, please. And once the scenarios were defined, we played around with adjusting the frequency of appliance use, what Liv has just explained, flow characteristics of fixtures at like toilets, showers, taps, based on expected improvement in water efficiency. And the table that you see summarize these assumptions, show how, in principle, total household water use decreases across various scenarios. Next slide, please. And once we developed like these different scenarios, 3 different scenarios, 190 and 80, we tweaked the PySimdium code, then we were able to actually connect drink water model with sewer model. So for hydraulic modeling, we use software which is called InfoWorks Water Supply Pro. And for the sewer modeling, we use a software which is called InfoWorks Integrated Catchment Model. And as a heart of the system, actually, are demand patterns developed by SIMD. To assess low demand conditions properly, we had to tweak the models a bit because the models that we received from Anglian Water were not detailed enough. So models didn't include like customer points, but they included like aggregated water demand. So when you see on the what you see on the left side, sorry, asterisks represent like aggregation of several houses in the in the area, while what we needed for Simdium in the current state is to have like customer points in the system. So what we did, we actually modified model. So we manually implemented around 850 customer points in the system. So what you see on the right side with so many different asterisks is actually all of those, every asterisk represent one property or one customer point. Next slide. Similar approach was applied to InfoWorks ICM wastewater model. The original model contained large aggregated subcatchment, limiting in principle application of Pycyndium. We manually added around, again, 850 property level subcatchments to actually better to be able to model and use SimDium. And in principle, this allowed us to assess low flow impacts in the sewer networks in greater detail. Next slide, please. So before analyzing, I will like to just walk you briefly. So I have 10 minutes. No, I have 20 minutes more. Before analyzing future scenarios.
I think it's minutes, Liliana.
Oh, it's 10, sorry. Yeah.
We're 5 minutes over.
Okay. Before analyzing future scenarios, but drinking, normally speaking, when you're dealing with models, you need to see whether models perform very well. As we say, all models are wrong, some of them are useful. So actually, what we did, we compared Anglian models with the models that we made for Simdium patterns and consumption patterns of 150 liters per capita per day. On the left-hand side, you see the drinking water model performance in one pipe in the system, and on the left side, you see it for sewer systems. Basically, both models, there are certain differences in terms of the minimum flows in both systems, but maximum flows were predicted pretty well. And in principle, both the drinking water and wastewater models perform satisfactorily. So we were confident enough to continue with testing different scenarios. Next slide, please. So, yes. Then we then analyzed how the drinking water network performs under different demands. What you see is 150, which is like baseline scenarios, 100, 90, and 80 scenarios. Left-hand side is flow. What we see is, of course, when you have less water use, you also end up having less flow in your systems. And so as expected, lower demand reduced overall flows and velocity throughout the network. And at the same side, so velocity is on the right hand side picture up. And what we also saw that water age increased because of the lower flows. And those changes became more pronounced in the lowest scenarios, of course, and that may indicate increasing operational and water quality challenges. Next slide, please. So basically what scenario analysis show that reducing demand lowers flows and pipe velocities across the network. And under the lower demand scenarios, velocity fall below typical self-cleansing threshold, and the age rise considerably, and this creates various operational risks. Next slide, please. What we also did is that we explore how reducing pipe diameters could help improve hydraulic performance under low conditions. So here is the also figure showing like current standards, one size smaller pipe and two sizes smaller pipes. I also tested three sizes, but then I would end up with the negative pressures in the system. So I just wanted to show you the results from the like two sizes difference. So basically, the results show that smaller pipe diameters increase, so improves velocity profiles, and two size reductions, of course, provides better improvement. However, downsizing pipes, as said, can also introduce certain trade-offs, particularly around delivering fire flow. So in principle, pipe reduction can help mitigating certain issues, but it really needs to be carefully balanced within the wider system design so that we don't end up with more issues. Next slide, please. Similar analysis in terms of scenario analysis was carried out for the wastewater network under the low flow, low demand scenarios. Again, as demand decreases, velocity decreases, shear stresses decreases, and this is also more pronounced at the lowest, like 80 liter scenario. Next slide, please. And in principle, what results indicate is that future low flow conditions could create operational challenges for sewer systems because of lower velocities and shear stresses. There is an increased risk of sediment accumulation, blockages, or the maintenance issue. And that is probably more pronounced under the lowest scenarios. And in principle, this suggests also that there must be a change how the system sewer design is approached. Next slide, please. So one of the last slides to explore possible mitigation measures. We tested both pipe diameter reduction and increased sewer slopes. I didn't want to test more than one size reduction because with sewer system you are also dealing with inflow infiltration. So in principle, you cannot really go very low, but in terms of the slope that I show you in the beginning of the presentation, you can play around. What you see is that both intervention improved velocity under low flow conditions, and what was also interesting to see is that increased slope had a stronger effects. As said, in practice, pipe reduction should be pipe size reduction should be limited to one size, two size maybe, because further downsizing increases sensitivity pretty much to inflow and infiltration. and it also reduces robustness, operational robustness of the system. And overall, the results so far show that there is no single intervention that fully resolves low flow challenges, and that the future sewer design will need to require a combination of different adaptive measures, which must be assessed case by case on a case by case basis. And to conclude, the next slide, please. To conclude, in principle, reduced water, as shown in many different figures, reduced water demand fundamentally changes the hydraulic behavior of both drinking water and sewer systems. Lower flows lead to increased water age and a lower velocity in drinking water networks, including which might lead to bigger operational risks, including stagnation, sediment accumulation, and also like potential quality deterioration. In principle, the modeling shows the same applies for sewer, so that lower flows leads to lower velocity and lower shear stress. So that can also lead to operational issues. The modeling results show that measures like downsizing of pipe diameters and slope adjustment can improve performance, but there is no single solution or like a silver bullet that will work everywhere. So in principle, future flow networks will require more adaptive, integrated, and case-specific design approaches. So you can use, for instance, this approach that we currently use, like including SIMDIUM, but cooperation between drinking water and sewer people is really needed in order to design those systems properly. What I also wanted to say that we came up with different scenarios that we tested, but in order to see whether people use water in another way in water smart developments, we are also in talking to Anglian and also other companies to get data and analyze actually how people use water in water smart developments, and if the scenarios that we developed make sense, because there is also concern from many different people that people would still use the same amount of water, that it doesn't matter whether you have a smart appliance or not, that average drinking water use per person would stay in the same range as it was so far. But that will be something that we will probably include in the report, and the report will be online, I think, in 2 weeks, and we will share report with all of you. Thank you very much for your time.
Thanks so much, Liliana. So just over to me to talk about the next steps for enabling water smart communities before we do move into the Q&A. And just with regards to the project itself, as Liliana's mentioned, the report we'll be sharing with our technical steering group today, and then following their review, we'll be looking to share that by the end of the month. And we will be sharing that alongside the link to this recording, which will all be on the Enabling Water Smart Communities webpage. So moving on to the next steps for enabling water smart communities. So as Vicky's alluded to, the programme is coming to an end at the end of June, and what we are going to be doing is transitioning into a community of practice. So this will build on the active group of stakeholders that's been grown through the Enabling Water Smart Communities programme to ensure that the delivery of integrated water management in all new developments is continued. The community of practice will be managed by SIWEM, who are the Chartered Institute of Water and Environmental Management, and they've also been a key delivery partner on the Enabling Water Smart Communities programme. As you can see here, the community of practice has 4 objectives. So the first being to bridge policy and practice by ensuring strategy and policy are informed by delivery experience. The second, to grow and sustain a diverse network of practitioners across housing, water, environmental sectors who actively lead, influence and implement integrated water management. The third is to facilitate practitioner-led peer-to-peer learning and curate a living knowledge base of tools, guidance and case studies. And the fourth is to drive the implementation of integrated water management by identifying opportunities and barriers in delivery. So the community of practice will run alongside the Water Smart Growth Board, and it will inform the Water Smart Growth Board. So the Water Smart Growth Board was launched on the 26th of March as part of the sort of transition event that we held at the Building Centre. And this cross-sector group has been established to support the development and implementation of relevant water and housing policy objectives, collectively contributing to the achievement of sustainable housing delivery. The chairs of the board include DEFRA and a housing industry leader, currently Fakenham, and the secretariat for the board is the Future Homes Hub. And under the board, as you can see on the image here, we will have some implementation groups, which will be special purpose task and finish groups, which will be established to deliver integrated water management initiatives as directed by the board and alongside the community of practice. So these 2 entities will be what forms the Enabling Water Smart Communities new operating model and takes the work forward once the programme does conclude in June. So just if you do want to hear more or be part of the community of practice, then please do scan this QR code. We want to encourage a wider network of professionals to get involved in this and be part of the drive for sustainable water smart homes. We are in the process of developing our plans for the community of practice. So yes, please scan this code to stay in touch and hear the latest news and sign up to our newsletter. Which now brings us on to the Q&A. So if you do have any questions, then of course, please do use the Q&A function on Zoom or raise your hands. And we would love to hear from you. I do believe we do have some questions in there. So just having a look. I think we've had some questions around the modelling itself, Liliana. So I'll try and combine because I'm conscious we've got 5 minutes. So we've got a question around whether the modelling factored in sewerage strength and less water use, reducing the dilation. I did see another one. Whether we've modelled removing rainwater. I think, yeah, if you want to come in there, I'll have a look through the rest. Oh, I think, are you on mute, Liliana? I can't hear you.
I'm sorry. We only model separate sewage system, which I forgot to. So we haven't modeled like combined, where you will have also rain in the system. So only like a sewer system, like separate sewer system, were modeled. In terms of the strength of the wastewater, that is already included in SIMDIUM. And for instance, Olivia, during her PhD, also did developed modeling nitrogen, phosphorus, COD, and BOD. So basically, based on the different scenarios, you can also see how much of the different pollutants you have in your system, if that makes sense.
Yeah. Thanks, Liliana. I've spotted one. We've got a question here from Nithya around whether the Pycindium model can be used to measure flow or water usage in a household and analyze different flows and usage when different fittings are used. I don't know if this is more a question for yourself, Liliana, or perhaps whether Olivia wants to come in. It's not been specified.
I don't see the question. Sorry.
So I'll it's from Nithya Thomas, and she's just asked, so can the Piscindium model, can this be used to measure flow or water usage in a household and analyze different flow and usage when different fittings are used?
You cannot measure, but you can predict, because it's a tool that generates patterns. But you can use, for instance, smart meter data to actually see how well you're producing these patterns. And for the sewerage, then you can assume that 0.85 to 0.9 out of the drinking water will become sewerage, actually. Olivia, if you want to add something.
Yeah,
extra.
no, just that absolutely you can use it to look at different fittings. Like that's the key benefit of it, that you can simulate the use of different fittings that you can specify within there.
Yeah, but not measure, only
Not
predict,
measure,
simulate.
predict, simulate,
Lottie, can we pick up George's point on this is not to be anti-water efficiency, this is just about pro scenario testing when you have water efficiency scenarios. Liliana, maybe you want to pick that up, that it's just about understanding the impacts. This is what this modelling was about as part of this programme, and it's not to discourage water efficiency. We want to actively encourage water efficiency, but think about your networks when you do these programmes. That's the sort of main message we want people to take away, isn't it?
Yeah, and especially because you're designing system for next 60, 70 years, you really need to design it properly so that you don't end up with operational problems. So definitely not against water efficiency, but about really looking at the system from more like integrated way, looking at drinking water side, looking at wastewater, and I think SimDium is a perfect tool to do so.
Great. Thank you so much. And then I think we've got time for one final question. So Brian Reed has been in touch to ask whether will climate change increase outdoor use due to increased garden watering? So I suppose it's a question of whether we factored this in. Does anyone want to come in on this?
It will definitely have an impact on gardening, but in this study we only actually included like home appliances and limited water reuse, so we didn't look into outside tap water, so only inside taps were modeled.
Okay, wonderful stuff. Well, I think we'll draw to a close there. So thank you so much, everyone, for joining and for your questions. Should anything else crop up, if you'd like more information or any further questions, then do just reach out. All of our contact details are at the bottom of the screen. But yes, thank you all for joining, and I hope you all have a lovely rest of the day.